Hi, I'm Peter Haines from the Geological Survey of Western Australia. Welcome to my talk. Eolian dune landscapes are common on planets and satellites with an atmosphere, and on Earth were presumably more common before the evolution of land plants. While Eolian deposits themselves are relatively common on Earth, preservation of ancient dune landscapes is rare. Here I will be illustrating an example from the Cambrian of the Officer Basin in Western Australia, where an ancient dune field is apparently preserved beneath flood basalt and can be imaged using aeromagnetic data. So this map shows the Officer Basin, and you can see that about 2/3 of it lies in Western Australia. I'll be showing some outcrop photos from right up in the northwest, around the Durbar and Table Hills. I'll show some pictures of drillcore from 3 GSWA stratigraphic wells, Lancer 1, Empress 1A, Vines 1, and I'll be showing aeromagnetic patterns from that area indicated in the red box. So now a brief introduction to Western Officer Basin stratigraphy. Deposition of marine and non-marine deposits began in the Toynian period of the early Neoproterozoic and continued into the early Paleozoic. It included cryogenic and glacial deposits, but here I'll be focusing on a thick package that's shown in yellow of Ediacaran to Middle Cambrian non-marine siliciclastic units. These units were deposited broadly synchronously with the contiguous Petermann and Patterson orogenies, which created mountain belts to the north, from which much of the sediment was derived, based on detrital zircon studies. I won't mention all the stratigraphic names beyond the McFadden Formation that outcrops in the northwest and the Lungkarta Formation known only from drilling under cover further east. These units were probably contiguous. They are dominated by sandstone deposited under Aeolian conditions, but include fluvial and playa intervals as well. I'll also point out the fluvial Durbar sandstone because it features in upcoming photographs. Finally, this package is overlain locally by flood basalts of the Table Hill Volcanics, a component of the Kalkarindji Large Igneous Province. So this map shows the distribution of the Kalkarindji Large Igneous Province, covers a large part of northern and northwestern Australia. During the Cambrian, we've now got fairly good dates on the Kalkarindji Large Igneous Province, and the mean age is around about 511 MA based on both argon-argon and uranium-lead dating. So the Kalkarindji Large Igneous Province mainly consists of the Antrim Plateau Volcanics up in the north, and down in the south in the Officer Basin and surrounding areas it consists of the Table Hill Volcanics and various feeders to the Table Hill Volcanics. Not much of that actually outcrops. The distribution area down there is mainly from aeromagnetic data and drilling. These plate reconstructions are just thrown in to show that the Officer Basin, which is shown by the red star there, was in relatively or mid to low northern latitudes between the end of the Cryogenian and the late Cambrian. So it was drifting slowly southwards across the belts that contain the major sandy desert areas of the world today during the time period we're looking at here. So here's a outcrop photo of the McFadden Formation. This is up in the Table Hills area. You can see very steep dipping foresets there in a sort of a metre or 2 metre thick bed, but relatively small scale Aeolian features like this are dwarfed by the scale of some of the outcrops. And in this photo here you see the contact between the McFadden Formation, which is sort of dipping to the left there, with the fluvial Durbar sandstone. And originally, when this was described, it was assumed to be an angular unconformity with the McFadden Formation tectonically tilted before deposition of the Durbar sandstone. But re-examination of this area indicates that in actual fact those deeping strata there are massive Aeolian crossbeds. Here's another picture of the same area. There's the Durbar sandstone at the top, sitting over these dipping foresets in the McFadden Formation. Another one again, same area. Here we're down at the bottom of the hill looking up the dip of the foresets that at this location are in excess of 50 metres in thickness, because they, even though they're starting to sort of flatten out at the bottom of the hill, they're still probably a bit more buried beneath the terrain. Yet another one, big foresets dipping off to the right, to the left there. Now let's go and look at some drill core. These sandstones here are in GSWA Lancer 1. This is the Lungkarta Formation, which doesn't outcrop at the surface. But here the strata appears to be dipping, but the stratigraphy both above and below this interval indicates that there's effectively no tectonic dip in the area. And in fact, the dip direction changes from time to time. It's, for example, shown by the red arrow there. So these are just massive foresets. And individual foresets reach up to 30 metres in thickness. They dip up to 30 degrees or so. The sediments are very well sorted, well rounded, typical of Aeolian deposits, and there are other features in them that are also typical of Aeolian deposits, such as reversely graded translatant strata. So when wind deposits sand by by wind ripples, it actually produces very slightly graded, reverse graded beds, and these are sort of typical of Aeolian deposits. So we see all of these features in there. We also occasionally see some interbeds of other facies that are perhaps interdune deposits, perhaps some playa deposits and things like that, and the odd fluvial bits and pieces, but it's mostly appears to be Aeolian. Here's another one. This is from GSWA Vines 1 over near the South Australian border. Again, the beds are often dipping, but every now and then you'll find a break, for example, indicated by the arrows there, where the dip direction changes. And these are once again interpreted as very large Aeolian foresets. This is from GSWA Empress 1, and here we've managed to core the actual contact between the Table Hill Volcanics and the underlying Lungkarta Formation, and the actual contact was right at the break between two core trays here. So in the top core tray you see Table Hill Volcanics, which have a vesicular basalt at the base. There's actually dating from this particular hole, as well as from other locations, for example, some of the feeder dikes. And then at the bottom you see the top of the Lungkarta Formation, and it's a baked contact with the sandstones being somewhat bleached there, but it grades down into a typical Aeolian facies underneath. Now if we go and have a look at some aeromag images, this is from that area I indicated in the box before. And now up in the northern part of the area there, you'll see a sort of a strange striped sort of banded pattern, but it's fairly vague. Now this is a total magnetic intensity image. When we run a filter over it, and this is a first vertical derivative filter which enhances relatively near surface the relatively near surface magnetic signal as opposed to the deeper signal, it suddenly comes out in stark relief. and you can see that strong banded, almost sawtooth-like pattern. And I interpret this as indicating basalt flowing down into dune corridors. Now I'll go and focus in on that little area there. I'm interpreting here that the basalt was flowing in a southward direction. The basalt itself is quite bright, and that was flowing down the interdune corridors, and the dune crest, which was not being topped by the basalt at this particular location, is quite dark because it's not the sandstone is not magnetic. This is another image from the blown up part of the northern, a bit to the north east of the previous image. In this area you don't see the same sawtooth effect, but you can see distinctive ridges and sort of tuning fork type junctions typical of Aeolian environments. In this area it's possible that the basalt is actually topping over the tops of the dune crests, although it's much thicker in the dune corridors, and they show up better. And just out of interest, if we superimpose the modern day topographic map image, you'll see that the modern day area also contains elongate dunes of a fairly similar scale, roughly a kilometre or so spacing between dunes, although I think the actual type of dunes in the modern environment, these relatively low vegetated dunes in the area are quite different from the probably much higher dunes in the Cambrian. Now we can go and Google Earth's a wonderful tool. We can go around the world and look for analog dune patterns, and I found a number of them in places like the Sahara. But these particular dunes that are in the Rub Al-Khali sand sea of southeastern Saudi Arabia, and I hope I pronounced that correctly, are particularly good analogue for the dune patterns of the Western Officer Basin. And you notice I've rotated this image for about 90 degrees, so north is to the is heading to the left. There's a north arrow down in the bottom corner there. I've just done that so that I've got the same orientation as the examples from the Officer Basin. Now I'm just going to zoom in here a bit into the middle of that area, and the dune fields in this area have been quite well studied, and from a paper that I'm listing over on the side there, 2013 paper, we note that studies of the area reveal that the prevailing wind direction, indicated by the blue arrow there, is actually somewhat oblique to the dune crests, which are described here as compound linear ridges. So the compounds, they're consistent of smaller, almost sort of Barken-like dune components that are actually oriented with the prevailing wind direction. Now we can try an interesting little experiment here, as the thought experiment. We can imagine some basalt flowing down those dune corridors. So there it is. I've put the basalt in green. It's a relatively thin flow, so it's not topping over the top of the dunes, but you notice the distinct shapes it produces, a fairly straight edge on the western side of the dunes, and the sort of rather cuspate sawtooth sort of pattern on the other in the other side. So now I can go back. Let's now return to our Officer Basin image. We can use the modern analogue to attempt to interpret what was happening in the Middle Cambrian in the Officer Basin. I will point out at this stage that there is a bit of a difference in scale. The dune spacing in the Officer Basin case is around about 1.5 kilometres. In the Saudi Arabian case, it was significantly more like 3 to sometimes 4 kilometres. So there were larger scale dune features, but otherwise they're quite similar. So we can use the asymmetry in those sort of sawtooth patterns there to suggest that the prevailing wind direction was from essentially west to east, a bit oblique to the linear dune migration direction. The basalt was moving from south to north, as I've said before, and another interesting feature is that the basalt flows tend to sort of die out at around about the same point, and I'd interpret this as some sort of inflection in the basin floor parallel to the basin margin, which is not that far away. Another possibility is that it's an erosional edge, but certain irregularities in it suggest that it's more likely to be a real original feature. Now to my conclusions. In this talk, I've illustrated the extensive Aeolian deposition occurring during the Ediacaran to Middle Cambrian of the Western Officer Basin. These were deposited at a time when the Officer Basin was at the typical latitudes of modern hot deserts, and the sand appears to have been sourced from adjacent mountain ranges. The deposits are impressive in outcrop, with foresets that likely exceeded 50 metres in thickness preserved locally. Given that only the lower part of dune bed forms are normally preserved, this is particularly impressive. Such deposits are also more widespread in the subsurface, as indicated from drill cores going as far east as the vicinity of the South Australian border. I've also shown that flood basalts have the ability to effectively freeze the entire dune landscape. In this case, allowing it to be imaged with aeromagnetic data because of the magnetic contrast between the magnetic basalt and the non-magnetic dune sandstone. While these Aeolian formations were previously poorly dated, and the start of deposition is still somewhat poorly constrained, we can now precisely date the deposits that lie directly beneath the Table Hill Volcanics, as deposition must have been still active at the time of basalt extrusion at around about 511 MA in the Middle Cambrian. We can use modern analogues, in this case somewhat larger scale dune fields in Saudi Arabia, to infer the type of dunes, their orientation and paleo wind conditions. This preservation mechanism might be applicable elsewhere on Earth and other planets. In fact, similar, though not as well preserved aeromagnetic patterns are locally visible in geophysical data over areas of subsurface antrim plateau volcanics in the Northern Territory, although I didn't have time to illustrate these in the talk. The antrim plateau volcanics is also known to overlie Aeolian deposits. This concludes my talk. Thank you for listening.